Salt water will float the Navy ships, but every ship needs large quantities of fresh water for its men and the ship's needs. Combat ships can't be equipped to carry enough fresh water for long periods at sea. A 30-day supply would require an enormous storage space and would weigh more than half as much as the ship. So the Navy uses distilling plants to make fresh water from seawater. A distilling plant and storage tanks for a 2 or 3-day supply requires very little space. But since the ship needs a continuous supply of fresh water, it is important to keep your distilling plant in good operation. Otherwise, the ship cannot run and you cannot live long without fresh water. This film will explain the basic principles of the low-pressure, steam-operated distilling plant so that you will be able to understand your job better. The basic principles that underlie the operation of this plant are heat transfer, evaporation and condensation, and the effect of pressure change on boiling temperature. Let's start at the beginning and see how we make fresh water from seawater. When flame is applied to a vessel containing water, the heat is transferred to the water because the flame is hotter than the water. Heat always flows from a warmer substance to a colder substance. This is called heat transfer. Let's use steam as the source of heat. The steam is hotter than the water, so its heat is transferred to the water. As heat is added to the water, its temperature increases until the boiling point is reached. The steam given off is called vapor to distinguish it from the steam that supplies the heat. Continued addition of heat causes boiling to continue, but there is no further rise in temperature in either the boiling water or the vapor. The vapor is piped off into a container. If the container is cooler than the vapor, heat is transferred to the container. The vapor will condense. That is, it will again become water. The water so obtained is called condensate, or distillate, or distilled water. The evaporator is the vessel in which the water is boiled. The condenser is that in which the vapor is condensed. The temperature at which water boils is affected by pressure. This is important. Let's say it again. The temperature at which water boils is affected by pressure. It is a fact that water boils at a lower temperature at high altitude than at sea level. This is because the pressure is less, and the air is thinner at higher altitude than at sea level. At sea level, water boils at a temperature of 212 degrees Fahrenheit. The higher the altitude, the lower the boiling point. This means the lower the pressure, the lower the boiling point. Pumping air out of the evaporator and condenser has the same effect as increasing the altitude. That is, lowering the pressure. As air is pumped out, the pressure lowers and the boiling temperature lowers. This process of pumping out the air is called creating a vacuum. A vacuum is the opposite of high pressure. The vacuum is read on a vacuum gauge. High vacuum means low pressure, and that means low boiling point. However, air pressure is not the only pressure to be considered. In a closed system, pressure due to vapor will likewise affect the boiling temperature. If the vapor is not condensed as fast as it forms, it will accumulate, create pressure, and lower the vacuum. This will raise the boiling temperature. If we pipe cold circulating water through the condenser, the vapor will condense faster. When the vapor condenses this way, the pressure decreases. When the vapor condenses as fast as it forms, the vacuum and low boiling point remain constant. Thus, boiling temperature is lowered by creating a vacuum, and the vacuum is maintained by the cooling effect of the condenser. Now we have illustrated the three principles: heat transfer, evaporation and condensation, and the effect of pressure change on boiling temperature. Let's develop a simple single effect distilling plant. The circulating water used to cool the condenser is seawater. It is pumped in, passes through the condenser, and then overboard. The condenser is called the distiller condenser to distinguish it from other condensers aboard ship. An evaporator feed taken off the circulating water line replenishes the water that is boiled away in the evaporator. An adjustable back pressure valve permits the right amount of feed water to be supplied through the feed line. The evaporator feed runs through the distiller condenser. Some of the heat of the vapor in the distiller condenser is transferred to the cool feed water and preheats it. The remainder of the vapor's heat is absorbed by the circulating water, which is discharged overboard. The air ejector is a device used to remove air from the system. Steam from the ship's supply operates the air ejector. A condenser called the air ejector condenser condenses the air ejector steam into liquid so that it may be returned to the ship's main feed and condensate system. The air escapes through vents. The evaporator feed is the cooling element in this condenser. The heat in the air ejector steam is transferred to the feed water. Thus, the steam is condensed and the feed water is heated. So we see how the principle of heat transfer is employed in the air ejector and distiller condensers. Heat from the vapor and the steam is saved and used to preheat the incoming feed water. Thus, very little additional heat is required to bring the feed water to a boil. The seawater, of course, contains salt and other impurities. As the vapor passes off, it leaves the salt and impurities in the evaporator. The water left behind becomes increasingly salty. This water is called brine and must be pumped overboard continuously. A proper water level is maintained by the incoming feed water. To maintain a constant production of distilled water, it is necessary to supply a fixed amount of steam to the evaporator. The amount of steam supplied is controlled by placing an orifice in the steam line and then maintaining a steady pressure above the orifice. The orifice is a circular hole in a plate inserted in the steam pipe. With a steady pressure above the orifice, the flow of steam to the evaporator will remain practically constant. The steam, after passing the orifice, will condense as it gives up its heat to the water in the evaporator. Some air may be mixed with the steam. Air will not condense. It will accumulate and eventually prevent the entrance of steam unless it is carried off. In order to prevent the accumulation of air, a pipe or vent is run from the steam space to the evaporator shell. The air is withdrawn through this vent. The air ejector removes it from the system along with the air and gases that come in with the feed water. So far, we have not considered the purity of the distilled water or condensate. The plant must not only produce enough condensate, it must produce pure condensate. As you know by now, the seawater in the evaporator contains salt and other impurities. The vapor, as we have seen, leaves most of these impurities behind. However, rapidly boiling water throws off tiny drops of impure water which may be carried along with the vapor. These tiny drops may be carried over by the vapor into the condenser. They will contaminate the condensate with salt. The impurities are called carryover. If there is too much carryover, the system is said to be priming. Unless priming is prevented, the water will be unfit for use. The place to stop the carryover is, of course, in the evaporator. Baffles and separators are used to do the job. Baffles do not hinder the flow of vapor, but the drops of water hitting the baffles are trapped. They accumulate and drain back into the boiling water. Too high a water level may cause priming. Priming may also be due to allowing too much salt to accumulate in the boiling water. This is avoided by draining off the brine at the proper rate. In this single effect distilling plant, 1 pound of steam will produce slightly less than 1 pound of water. In this single effect distilling plant, 1 pound of steam will produce slightly less than 1 pound of water. We can combine 2 of these plants in series so that 1 pound of steam will produce nearly 2 pounds of water. Such a combination is called a double effect distilling plant. A double effect distilling plant employs 2 evaporators, one known as the first effect and the other the second effect. The vapor generated by the first effect is piped through the second effect. The water in the first effect is boiled by the steam. The water in the second effect is boiled by the vapor. The vapor is not as hot as the steam, but it is hot enough to boil the water because a higher vacuum and consequently a lower boiling point is maintained in the second effect than in the first. The feed water passes through a vapor feed heater. Here it picks up additional heat. The heat comes from the vapor after it leaves the first effect and before it goes to the second effect. The feed water in the second effect is brought in from the first effect. This is an added heat economy because this water has been boiled in the first effect. The condensate from the two effects is combined and sent to the ship's freshwater supply tanks. A double effect plant will produce almost twice as much distilled water per pound of steam as will a single effect plant. The two effects may be combined in a single shell, thus saving space. More space and heat are saved by placing the distiller condenser and the vapor feed heater inside the shell. When assembled and before being covered with insulating material, a typical double effect distilling plant looks like this. This model has an output of 4,000 gallons per day. Within the shell, we see the first effect evaporator, the second effect evaporator, and the partition which separates them. These bundles of pipes are called tube nests. They conduct the steam and vapor through the two effects. Tube nests are shown this way on the diagram. A tube nest is made up of a number of pipes or tubes. Their ends are secured into tube sheets. Over the tube sheets are heads, front and back. This assembly is called a tube nest or tube bundle. Steam or vapor is admitted into the front head and enters the upper tubes. A division plate in the front head blocks off the lower tubes. The steam or vapor passes through the tubes to the back head. By the time it returns to the front head, practically all of it is condensed. The condensate enters the head under the division plate and is piped off. The tube nest in the first effect carries steam supplied by the ship's auxiliary exhaust system. The tube nest in the second effect carries the vapor generated by the first effect. Both tube nests are submerged in the boiling feed water. Tubes are also used in the vapor feed heater, the air ejector condenser, and the distiller condenser. However, in these, the feed water is inside the tubes and the vapor or steam surrounds the tubes. Here are the baffles and the vapor eliminators or separators which make up the moisture elimination system in the two effects. Pipes drain the liquid back to the boiling water. This flow diagram shows the essential features of the plant. There are various other parts to be added to complete the system. The circulating seawater passes through a condensate cooler. Here it cools the condensate before the condensate is sent to the freshwater tanks. Two air ejectors are provided. One is used for standby. The vapor from the first effect passes through the second effect tube nest, condenses, and leaves through a drain line. This condensed vapor is called the second effect tube nest drains. A drain regulator is used in the second effect tube nest drains. This regulator allows only liquid to pass through it. The vapor is forced to remain in the second effect tube nest until it is fully condensed. The condensed vapor from the second effect leaves the shell through the distiller condenser drain line and is called the distiller condenser drains. Different pressures exist in the two drain lines. The pressure in the second effect tube nest drains is higher than the pressure in the distiller condenser drains. In order to combine the drains, it is necessary to equalize their pressures. A flash chamber is used in addition to the drain regulator to combine these two pressures. The second effect tube nest drains leaves the drain regulator at a lower pressure than when it entered. It therefore partially flashes into vapor. This vapor must be separated from the liquid and recondensed. Separation takes place in the flash chamber. From here, the vapor is drawn out by the vacuum into the distiller condenser. Here it is condensed. It returns as liquid to the flash chamber. As the condensate from both effects collects in the flash chamber, it is pumped out. This pump is necessary because the system is under vacuum. After being pumped through the condensate cooler, the distilled water enters a test tank, and from here on it is called distillate. The test tank contains two compartments. The distillate in each compartment may be discharged to the bilge or pumped to the storage tanks, depending upon its purity. Sampling cocks are provided so that the distillate can be withdrawn and chemically tested for its salt content. In the steam supply line is a weight-loaded regulating valve which maintains the required 5 pounds of steam pressure above the orifice. A drain pump withdraws the condensed steam from the first effect tube nest. The vacuum in the tube nest makes it necessary to have this pump. A drain regulator keeps the steam in the tube nest until it is fully condensed. The drain regulator also maintains a steady liquid level at the pump. There is a brine pump which withdraws the brine from the second effect evaporator. It is necessary to have a constant discharge of the accumulated brine because there is constant feed and constant evaporation. The plant includes valves, thermometers, strainers, pressure gauges, and gauge glasses for observing water levels. There are also electrical salinity cells which show the salt content of the condensate at various points. Also, there is testing equipment for testing the brine. Let us take another look at the plant itself and see what some of the parts look like. Circulating water enters the distiller condenser here. This is the back pressure valve, and this the takeoff for the evaporator feed water. These are the air ejectors. This the air ejector condenser. Steam from the ship's auxiliary exhaust system enters the first effect tube nest here. This is the drain regulator for the first effect tube nest. This pipe carries the vapor from the vapor feed heater to the second effect tube nest. This is the drain regulator for the second effect tube nest drains. This, the flash chamber. The distiller condenser drains, leaves the distiller condenser here. The test tank and the condensate cooler, as well as some of the pumps, are not always located close to the plant. This water gauge permits reading the water level in the second effect evaporator. A sight glass permits viewing the boiling water within the evaporator. A similar water gauge and sight glass are on the other side for the first effect. Now let us trace the flow of water, steam, vapor, and condensate. Seawater, which we call circulating water, is pumped in and passes through the condensate cooler, where it cools the condensate. It then passes through the tubes in the distiller condenser, where it condenses the vapor from the second effect. Leaving the distiller condenser, most of the circulating water is discharged overboard. A back pressure valve permits the right amount of feed water to be supplied through the evaporator feed line. The feed runs through the distiller condenser, where it picks up some heat. It then goes through the air ejector condenser, where it picks up more heat and at the same time condenses the steam in the air ejector condenser. It then goes through the vapor feed heater, where it picks up still more heat before it enters the first effect evaporator. All that is not evaporated passes into the second effect. The brine is pumped out and discharged overboard. Steam from the ship's auxiliary system is passed through one of the air ejectors. The flow of steam creates suction in the air line and pulls air out of the system, creating a vacuum. The air and steam, mixed, enter the air ejector condenser. The air escapes to the atmosphere through vents. The steam heats the evaporator feed and at the same time is condensed and returned to the ship's feed and condensate system. Steam from the auxiliary exhaust system passes through the weight-loaded regulating valve, through the orifice, and enters the first effect tube nest, where its heat boils the feed in the first effect. A drain regulator keeps the steam in the tube nest until it condenses. The condensate is pumped out and sent to the ship's feed and condensate system. The vapor produced in the first effect passes over baffles and vapor separators, then through the vapor feed heater, where it helps to preheat the evaporator feed. It then passes into the second effect tube nest, where it boils the feed in the second effect evaporator and at the same time is condensed. The second effect tube nest drains passes through a drain regulator, which passes only liquid. As the liquid leaves the drain regulator, some of it flashes into vapor because the pressure has been reduced. This mixture enters the flash chamber. Here, the vapor is separated out and goes to the distiller condenser, where it is recondensed and returned to the flash chamber. The vapor produced in the second effect passes over baffles and vapor separators and enters the distiller condenser, where it is condensed. The condensate, called the distiller condenser drains, flows to the flash chamber and mixes with the second effect tube nest drains. From here, the combined flow is pumped through the condensate cooler, where it is cooled by the circulating water, and into the test tank. From the test tank, the distillate is pumped to the ship's freshwater storage tanks. This completes the cycle. Now let's look at the complete system. When you understand the principles, you are ready to learn how to operate and maintain the plant. The size of the plant depends on the needs of the ship. Whatever the size, the principles are the same.